Our planet Earth is in constant motion, engaged in a celestial dance with the sun. This dance is not a simple waltz. It is a complex choreography of cycles, each influencing the amount of solar energy Earth receives. These cycles, known as the Milankovich cycles, are named after Serbian scientist Milutin Milankovich. He dedicated his life to studying their profound impact on Earth's long-term climate patterns. The Milankovich cycles are not responsible for the rapid climate change we see today. That is driven by human activities. However, understanding these cycles is crucial. They help us understand how Earth's climate has naturally changed over thousands of years. This knowledge provides context for present-day climate change discussions. Imagine these cycles as subtle variations in Earth's movements. These variations affect the amount and distribution of sunlight reaching different parts of our planet. Over very long periods, these seemingly small changes can have significant effects. They influence the advance and retreat of glaciers and the coming and going of ice ages. The Milankovich cycles are a fascinating area of study. They remind us that our planet is a dynamic system, constantly changing over time. Earth's journey around the sun is not a perfect circle. It is an ellipse, a slightly stretched out circle resembling an oval. The degree to which Earth's orbit deviates from a perfect circle is called eccentricity. A high eccentricity means a more elongated oval. A low eccentricity means the orbit is closer to a circle. Now imagine this oval shape changing over incredibly long periods. This is exactly what happens with Earth's orbit. The eccentricity of Earth's orbit cycles between being more elliptical and more circular. This cycle takes roughly 100,000 years to complete. Why does this matter for Earth's climate? The answer lies in the varying distance between Earth and the Sun throughout the year. When Earth's orbit is more elliptical, there's a greater difference in the distance between the two at different points in the orbit. This means that at times Earth receives significantly more solar energy than at other times. This variation in solar energy received has a direct impact on Earth's climate. It can lead to more extreme seasonal differences with hotter summers and colder winters. Over thousands of years, these changes can contribute to the growth or melting of ice sheets, influencing global climate patterns. Picture Earth spinning like a top. It's not perfectly upright, but tilted on its axis. This tilt, known as obliquity, is what gives us our seasons. The angle of Earth's tilt, however, is not constant. It changes over time, like a rocking chair slowly swaying back and forth. The obliquity of Earth's axis oscillates between approximately 22.1 and 24.5 degrees. This cycle takes about 41,000 years to complete. When the tilt is greater, the poles are pointed more directly towards or away from the sun at different times of the year. This leads to more extreme seasons. Summers are hotter and winters are colder, particularly at higher latitudes. These changes in obliquity have significant effects on Earth's climate. When the tilt is greater and summers are hotter, ice sheets can melt more rapidly. Conversely, a smaller tilt can lead to less seasonal variation and contribute to the growth of ice sheets. As Earth spins on its axis, it also wobbles slightly like a spinning top. This wobble, known as precession, is caused by the gravitational pull of the Sun and Moon. Precession causes Earth's axis to trace a circle in the sky over 26,000 years. As Earth wobbles, its axis direction changes over time. Currently, Earth's axis points towards Polaris. In 13,000 years, it will point towards Vega. This shift affects the timing of the seasons. It can cause milder summers and colder winters, or hotter summers and milder winters. These shifts, driven by precession, influence Earth's climate over long periods. They affect solar energy distribution and contribute to climate change patterns. Section 5. Evidence in the rocks unveiling the Milankovich cycles. The Milankovich cycles are not just a theoretical concept. We have concrete evidence of their influence on Earth's climate in geological records. These records act like ancient time capsules. Deep-sea sediment cores contain layers accumulated over millions of years. These layers preserve past climate's chemical signatures. Analyzing these sediments helps reconstruct past climate variations. Ice cores from glaciers offer a frozen archive of Earth's climate. These cores contain trapped air bubbles preserving ancient atmospheres. Analyzing these bubbles tracks changes in greenhouse gases. Climate change patterns align with Milankovich cycles. Glacial and interglacial periods match Earth's orbital variations. This correlation shows Milankovich cycles' role in Earth's climate. Section 6: Ice Ages, a testament to the power of orbital variations. The Milankovich cycles have left their mark on Earth's history most dramatically through the coming and going of ice ages. These periods of significant global cooling, characterized by the widespread expansion of ice sheets, are a testament to the power of orbital variations in shaping Earth's climate. During an ice age, vast ice sheets, sometimes miles thick, cover large portions of continents. These ice sheets reflect sunlight back into space, reducing the amount of solar energy absorbed by Earth's surface. This process further cools the planet, amplifying the effects of the initial orbital forcing. The Pleistocene epoch, spanning from about 2.6 million to 11,700 years ago, is a prime example of the Milankovich cycles in action. This epoch was marked by a series of glacial-interglacial cycles, with ice sheets advancing and retreating across the northern hemisphere. The timing and duration of these glacial cycles align remarkably well with the predicted variations in Earth's orbital parameters. This correlation provides compelling evidence that the Milankovich cycles have been a major driver of ice ages throughout Earth's history. Section 7: Milankovich cycles versus human impact, a tale of two climate drivers. While the Milankovich cycles have been instrumental in shaping Earth's long-term climate patterns, it's crucial to distinguish them from the rapid climate change we are currently experiencing. The current warming trend is primarily driven by human activities, particularly the burning of fossil fuels, and not by natural cycles. The Milankovich cycles operate over very long timescales, with cycles lasting tens of thousands to hundreds of thousands of years. In contrast, human-induced climate change is happening much more rapidly, over decades to centuries. The rate of current warming far exceeds anything observed in the paleoclimate record, indicating that natural factors alone cannot explain the observed changes. The primary driver of current climate change is the increase in greenhouse gases, such as carbon dioxide, in the atmosphere. These gases trap heat, preventing it from escaping into space and causing Earth's surface temperature to rise. The burning of fossil fuels, deforestation, and other human activities release massive amounts of carbon dioxide and other greenhouse gases into the atmosphere, amplifying the natural greenhouse effect and driving global warming. Section 8: The urgency of now understanding our role in a changing climate. Understanding the difference between natural climate variability, driven by factors like the Milankovich cycles, and human-induced climate change is crucial for addressing the current climate crisis. While natural cycles have shaped Earth's climate over millennia, the rapid warming we are experiencing today is unprecedented in human history and poses significant risks to our planet and its inhabitants. The impacts of climate change are already being felt around the world, from rising sea levels and more extreme weather events to changes in plant and animal life. These impacts are projected to intensify in the coming decades, posing significant threats to human societies and ecosystems. Addressing climate change requires a multifaceted approach that includes reducing greenhouse gas emissions, adapting to the impacts that are already occurring, and investing in research and development of clean energy technologies. It is essential to recognize that we are not passive bystanders in the face of climate change. We have the power to make choices that will determine the future of our planet. By understanding the science of climate change, supporting policies that promote sustainability, and making conscious choices in our daily lives, we can all contribute to creating a more sustainable and resilient future. Section 9: Continuing the exploration resources for further learning. The Milankovich cycles and their influence on Earth's climate are a fascinating area of study. If you're interested in delving deeper into this topic, numerous resources are available to satisfy your curiosity. Here are a couple of suggestions. Books: Ice Ages, Solving the Mystery by John Imbrie and Catherine Palmer. Imbrie, The 2 Mile Time Machine, Ice Cores, Abrupt Climate Change, and Our Future by Richard Alley. By continuing to learn about climate science and engage in informed discussions, we can work together to address the challenges of climate change and create a more sustainable future for all. For more great videos like this one, click like, share and remember, smash that bell for notification of more climate news like this.